In this video we're going to work out the double integral of this surface. So if you punch this into Google, it will give you this surface. So glancing at this, this dy here would imply that this is going to be y equals something, and this would mean x equals something, but then if you look at this, after a while you should have a hunch that this is some sort of circle, because if you rearrange this, it would be square both sides, so that would be y squared equals 1 minus this thing here, and then here you can see it is some sort of circle of radius 1. So what that means is this is the origin here, x-axis, y-axis. So you're looking at some sort of circle of radius 1, and then in the x direction you can see that you're integrating from x equals negative 1 and x equals positive 1, and then in the y direction, in the dy direction, it would be the positive strand. So that would be this positive strand here, and then this bit here will be the negative. There's a negative here. Will be your negative strand. So you're looking at this negative strand. So looking at this, you can see you're integrating over a region that is of a circle. So you're integrating over some sort of circle. Well, if you're integrating over some sort of circle, and there's some sort of circle associated with this, so you should think about converting this into polar coordinates. So converting, well, you're integrating over some sort of circle here, some sort of circle here, and that's x squared plus y squared. So you should be thinking about polar coordinates. So let's convert this into polar form. So polar form, hang on. So remember, polar form, it would be r dr d theta, and double integral. If you look at this, it's going to be r first, so it's going to be r equals something, and then it would be the angle, theta equals something, and your volume here. So now now we know that this is a circle of radius 1. So this is a circle of radius 1. So hang on. So this is some sort of circle of radius 1. So really you're integrating from a radius of 0 to a radius of 1. Because if you look at the xy domain, hang on, xy, so this is some sort of circle. So you're actually doing this, integrating from a radius of 0 to a radius of 1, radius of 0 to radius of 1, radius of 0 to radius of 1, radius of 0 to radius of 1, and so on. So you're going to scan through the whole region, and in terms of the angle, you're scanning from an angle of 0 all the way to an angle of 2 pi. So this would be 0, 2 pi. And then when you're converting from Cartesian into polar, always keep an eye out for x squared plus y squared equals r squared, and always keep an eye out for x equals r cos theta, y equals r sine theta. And I'm expecting you to know this by now. So here you've got r squared, so put that into here. So this is really r squared. So this whole thing here will be 2 over 1 plus r squared, and then you've got your squared on the outside here, squared on the outside here. So converting from Cartesian into polar will then take us to here. Okay, so we are currently here now. So now it's just a matter of integrating this thing here. So use whichever method you want. When you integrate it, it will then give you this. So when you integrate it, it will then give you this thing here. So let me give you a reminder of how to integrate from here to here. So integrating this, let's rearrange this so that it looks like this. And here you've got one block times another block. when you integrate it, you're looking for something in such a way that when you differentiate it, it gives you this. Well, notice that this is exact derivative of this thing here. So because this is the exact derivative of this thing here, I know it's going to be easy to integrate. So, well, use whichever method you want. Either use substitution or whatever. Because I know that this is the derivative of this, I know it's easy to integrate. So I'm just going to guess my way to the answer. So I know it's going to be one notch higher than this. Remember, I'm looking for something in such a way that when I differentiate it, it gives me this. Well, it's going to be one notch higher than this. So my initial guess would be this. 1 plus r squared, one notch higher would be to the power of minus 1. So when I differentiate this, it will then give me minus 1, and then the bubble stays intact, and then the power gets minused by 1. So that would be minus 2. But then I've got to times the derivative of the bubble itself, which will be 2r. So notice that this thing here looks very similar to this whole thing here. You've got your 2r here, and you've got your this thing here. But then the only thing that you don't want is this negative here. So you would go back to your initial guess and stick a minus into here. So now when you differentiate this, it will then give you, well, the minus will then disappear. It will then give you this thing here. So now this is exactly the same as this. So as I said earlier, use whichever method you want. You can just, because this is like the exact derivative of this, I know it's going to be easy to integrate, so I'm just going to guess my way to the answer. So when you integrate it, it will give you this. So this thing here is this thing here, and we're integrating from 0 to 1, integrating from 0 to 1. So now we are currently here. Okay, so hang on. So now now you would put this into here, so that would then give you this, and then take away and then put this into here. It will then give you negative 1. So now this thing here will then become the number half, and then now integrate this with respect to theta, so that would just give you a half theta. So that will then give you a half theta, and then now put 2 pi into here, that will give you pi. So the volume turns out to be pi. So if you're integrating over the region of a circle, the volume underneath this region, under this surface, is actually pi. Okay, so this is your final answer.